So, good morning again. Well, this is, of course, from our homes and not exactly from the department, and I hope you are comfortable at home as well. And so let's start this off. Today's title is The Future of Remote Handling of Materials by Robot. Ambitious title, but I think we hopefully say some interesting things here. So the brief structure will be, as it was announced, with more details here. The first is who is doing some HRI development in RAIN, basic principles for advanced HRI, then the technology of real-time work area modeling, then shared knowledge of procedures with the robot, and remote handling through VR, virtual interactions, and then reconfigurability by operators and operator training. The names of the presenters are beside the titles. So who is doing what on HRI in RAIN? Without names, but institutions, we have covered a range of topics which contribute to the HRI area: control of snake robots, gestures-based and novel haptic control by Manchester, Nottingham, Manchester, variable autonomy in remote handling, novel methods of robotic visual perception, audio and haptic interfaces for HRI, synthetic views and automated grasping, assessment of operator experience, and formalization integration of reconfigurable HRI, shared by a few institutions, Sheffield and Race mainly. And you can see here all the names of the institutions who do some work in these areas. Apologies if there was more activity than I realized, but things are developing fast at RAIN. Okay, sorry, the next slide. Yeah. So the first part of this webinar will be basic principles of advanced HRI. There are not many published articles actually about the principles, sort of generic articles. There were only a very few. There are lots of technical, detailed articles. So let me start off with what the aim was during the RAIN project at the very start. We wanted to develop augmented and virtual reality interfaces for human-robot interaction that allow variable levels of autonomy between operators and robots, of course, thereby to develop improved HRI interface systems with the purpose of easing the operation of teleoperated systems. So we have progressed on this, and there's approximate estimates of readiness level here indicated. Well, it's difficult to measure, but we made a progress. So the first question was there why to improve human-robot interaction? Well, it's strenuous for operators for long hours, error and accident prone, slow and low in productivity. If the work is repetitive with large amounts of materials, then it is not the best use of human resources. But still preferred the manual teleoperation, haptic teleoperation for complex manual handling where human decision making is important. So there are complicated operations where we certainly can't use robots today. How to improve human-robot interaction? Exactly by addressing the points listed earlier: make operators work less strenuous, sorry about the strenuous actually, enhance robotic productivity, reduce the number of operating personnel needed, make the robotic arm and sensor system easily reconfigurable by operators, and then provide human-like decision-making of robots. So how to make operators work less strenuously? By making the operator's decision easier through providing clarity of the work scene. So obviously one of the problems in haptic teleoperation is the precision of movements of grippers, and which may not be very clear to the operators. By novel methods of commanding, which are easy and quick to issue. So obviously if you have to do everything by your fingers, then that's not a quick and easy way to handle remotely objects. So enabling the issuing of more complex procedural commands. So that's a high level of autonomy, so that the whole procedure you would write down as we describe later, and the robot just does it as a technician would do. Introducing automated safety measures which reduce the likelihood of errors. Now this can be an inherent feature in the future of HRI. How to enhance robotic productivity by developing fast and precise automated modeling of the work area by the robot. So it's not that just the human understands what's in the visual scene, actually where the work is to be done, but the robot understands what is there. Sharing the robot's knowledge of the work area with the operator. Now it is like a feedback. The robot shows you what it perceived in the environment, and therefore you have a good understanding what the robot could do. Using this second point to enable high-level commands for the operator's supervisory role. So this is again a high-level autonomy, so that the operator gives high-level commands and won't supervise the work. Enable the robot to reason about dangers and use that in its action planning. Now, this could be important in case of delicate materials, or which can cause damage if they break and open up problems. How to reduce the number of operating personnel needed? Well, by switching to higher autonomy levels where current technology permits. So as we are more and more capable of developing higher level autonomy, the less and less number of people are actually needed, because everything is more automated. Sharing knowledge between the operator and the robot, because then the robots can do the work on their own. Writing down operational procedures in English, which are actually high-level codes for execution. Now, this is a novel feature you may be interested in. Expand the number of operational hours with reduced number of staff. So that's rather implication. Yeah. Use some of the leftover staff to write formal procedures in English for robots. Now that's something which is possible now. How to make the robotic systems easily reconfigurable? By not requiring operators to know any low-level programming knowledge, such as C++, Java, JSON, Gwendolen, Cortex, ROS. So I just listed some low-level programming languages here, which need to be avoided actually to be used by operators. Creating a system where the operators need for an IT person is only under exceptional circumstances. So that the operators don't need programmers to be around. And enable operators to use natural language synthesis to define system configuration and reconfiguration of robot sensors and actuators, including arms and their tooling, repairs, cutters, focus, using the suitable software. How to provide human-like decision-making of robots? By developing shared knowledge of the physical objects with robots, that certainly helps. Use anticipation of events by physical inference engines, so that means that in fact the robot can foresee what would happen if something is planned to be done. Writing down operational procedures in English, what is actually high-level code for it. So I mentioned this before. So expand the number of operational hours with reduced number of staff. So and use some of the leftover staff to write formal procedures in English for robots. So this is a summary on 3 columns: levels of interaction and autonomy in the first one. The autonomy level increases from the bottom to top in the rows of the table. The second column is for level of robotic perception and world modeling ability. So this is also increasing from bottom to top. A level of robotic planning, action, execution, and planning and action execution skills. Again, these are improving from the bottom to the top. So that's actually completes my part of the presentation at the beginning. It was an overview of the basic principles of advanced HRI. And would like to hand over to my colleague, who is a postdoctoral research associate at the University of Sheffield, Mohammed Hazim, or Al-Nuaimi. And he will talk to us, or to you, about the technology of real-time work area modeling, which I mentioned that it's quite an important thing. I would like to remind you that questions will be responded to at the very end of all the presentations. So here we go. I hand over to Mohammed, but I don't have a button for it, so please take over.
Yeah, thank you, Professor Sandor. I'm trying now to share my screen here. Okay, is it clear now?
Yeah, that's great.
Okay, thank you. Hello everyone, my name is Mohammed Al-Nuaimi. I'm a postdoc researcher at the University of Sheffield working for RAIN project. I'm going to talk now about the robot arm perception system for HRI, human-robot interaction. Here I will talk about point number 1 of part 2, the robot arm perception system. At the beginning, I would like to say that whenever we want to develop a good interactive system, a first requirement is that the robot should have a good understanding of its environment. So in this presentation, I'm going to talk about the robot perception system, which will perceive the environment. Unless this process done correctly, we will not be able to design a good interactive system. In these photos, we can see a mock-up rig of the glove box system that consists of the frame, the robot arm, a stereo camera, a computing device, and of course the nuclear waste objects. We are using Universal Robotics Arm, the UR5E, along with the robot gripper. We fixed a small size stereo camera on the top of the robot gripper to perceive the environment and provide the necessary data for the computing device to analyze and provide useful information for the robot reasoner or decision maker. So here we can use a personal computer for data processing, but we thought that it will be better to use this powerful and small size computer on board from NVIDIA, which is easy to attach to the frame of the mock-up rig and connect to the robot arm and the stereo camera. Before I go into the details of the presentation system, of the perception system, I would like to mention that we are using a real set of nuclear waste materials, similar to the one used by the National Nuclear Laboratory and Sellafield, which is actually provided to us by Sellafield, as we can see in this photo here. And this has been used by the National Nuclear Laboratory and Sellafield, which is almost the same set. The components of our perception system are the stereo camera, a method for object detection based on deep learning neural network, a method for objects identification and detection based on machine learning approach, a point cloud generation and segmentation, and finally a method for distance estimation between the gripper and the objects. This is the diagram of the real-time perception system. First, we get a continuous stream of images from the camera. This will provide the necessary data for 3 subsystems working together in parallel. And those are the recognition of known objects. I mean here by the known objects, those who have been previously identified by the system through the training process. In case there is a new or unknown object in the glove box, then the previously mentioned block will not be able to recognize that object. Here the system will give an indication to the operator to use another subsystem to manually identify this one here. In case there's a new object, then it will give indication to the operator to use another subsystem to detect the new object. First to identify, then to detect the new object and add it to the database so that it can be automatically recognized in the next time. Then we have the point cloud generation in this block here. This is the point cloud generation and segmentation. This step is used to generate 3D models of the objects to feed into the Unity virtual environment, which is this block here. Then we have also the distance estimation between the gripper and the object. The algorithm will first calculate the distance between the camera and the object. Because the camera is fixed on the top of the gripper, then the algorithm can calculate the distance between the center of the gripper and the object. This operation is vital for picking up the objects by the gripper correctly. The information generated above will go to both the Unity virtual environment to visualize the whole Globebox contents for the operator, also to the robot reasoner to decide what to do based on the available data. Here we have generated an augmented data set with annotation for the set of objects that we have. Then we have trained our neural network based on this data set to detect a set of objects. So I would like to play this video here. We can see a short video for the detection of objects using the deep learning approach by applying a mask around the objects, also to identify what kind of object it is and what's the probability of detection. Now we can say that the objects learned earlier by the robot are now tested for the reliability of recognition. The detection algorithm will give the probability of each detected object. Based on that, the robot reasoner will decide what to do with this object. One of the major drawbacks for deep learning networks is that it needs training with a large amount of data. Adding a new object to the system later while it is working means to start the training process again, which is annoying and time-consuming. Also, it is not always possible for the operator in the industry to go through such kind of process. Hence, we have took another approach by giving the operator an easy method to identify new objects manually during the system operation. Also, if the probability of detection in the previous step was low, or if the object couldn't be recognized by the deep learning method, then the system will give an indication to the operator to complete the operation manually. And this includes to identify this object by outlining each unknown object manually, to define manually the attributes and the class of the unknown object, and to move on to the next unknown object if there is any others. This operation needs to be done one time. Once the object identified, then it will automatically add it to the dataset, and the next time will be recognized automatically. Here in this video, we can see a model of our Globebox in RViz. At the beginning, the operator is defining a new object by typing the name and the class of the object. Then the robot arm will move to take a few photos of that object, and the operator will manually outline those new objects from different views, as we can see here. It will ask the operator if there's any more objects to identify. If not, then it will save to the database so that it can automatically recognize in the next time. So in this video, we can see this method, how it works exactly. So this is a feature-based and SVM method to detect objects by the operator. Before we watch this video, I would like to say that it's not an easy task to generate a point cloud for such small size objects. Now we will have a look at the real-time point cloud generation. Actually, due to the current lockdown, we couldn't access the lab, so I recorded this video on the table in my apartment. The stereo camera can generate a point cloud for objects from a minimum distance of 15 centimeters. Here we can see that the system is providing a stream of point clouds for the objects on the table. The system is also generating a trajectory of the camera path, where this is helpful while generating a 3D model of the objects. The system is also providing a depth map, as we can see in this window here. It's a dark colors, that's why it's not clear here. The depth map has been used to estimate the distance between the gripper and the objects, as mentioned before. So this is now a 3D model of the tabletop and the objects on the table, as we can see here. Those green and red arrows represent the trajectory of the camera while it was moving, and those are the models of the objects in point cloud. Here we can see one more important process, which is the point cloud segmentation. This process is important to separate the object models from each other and provide a useful data to the Unity virtual environment. The last step here is to estimate the distance and detect the orientation of the object from the generated point cloud. This operation is important for the gripper to know where to go and how to pick up an object correctly. So in this one here, we can see the distance estimation, and here we can see the object detection of object orientation. With this, I came to the end of my presentation. Thanks for you listening. We will have the questions session at the end if you have any. For now, I'll handle the rest of the presentation to my colleague James. So.
Okay, thank you very much, Mohammed. Let me just share my slides. So I hope everyone can see that okay. So I'm going to be covering sections 2.2 and 2.3 of the talk today. Section 2.2 is an overview of our work in developing a framework for robotic control, which enables both the operator and the robot to have a shared understanding of the system. So we call this a shared knowledge of procedures, and the framework we're using is based on the principle that a robot can be controlled through a hierarchy of sentences written in English, and we call this hierarchical meaning development. So the 4 questions I'd like to answer for you this morning are: how does hierarchical meaning aid procedural knowledge sharing between robots and humans? So to do this, I'll try to briefly explain both the concept of shared knowledge and the framework of hierarchical meaning. And then after that, I'm going to try and quickly answer questions 2, 3, and 4, which are how hierarchical meaning can increase in efficiency, enable reconfiguration, and support human teamwork. So, what is shared knowledge and why is it important? To kind of sort of start with, I'm going to ask you a simple question, and that is, how do you make a peanut butter and jam sandwich? Now, if I ask you to write me the instructions down, I'm sure for most of you, they're going to look pretty much exactly the same. Take 2 slices of bread, throw peanut butter on one, jam on the other, etc. But those of you who kind of sort of gone ahead and understand where I'm going with this might start to write down some quite precise instructions. Unscrew the lid of the jar, put the sharp end of the knife in the jar, and so on. But eventually you'll realize that no matter how detailed you actually go with these instructions, you can't make them unambiguous for me without assuming something about me. You either assume that I know what the sharp end of the knife is, or you assume that I know what putting that inside the jar even means. So in general, when you're giving instructions, you assume that the recipient has the knowledge to complete each of those instructions. You assume they'll complete them in order, and they'll complete them within some reasonable safe boundaries. With humans making a sandwich, those are all fairly reasonable assumptions, I'd hope. With robots, it's just not possible to make those assumptions. Like, they're not adaptable, they're not capable of reasoning in the same way that humans do. And for this reason, not only do we have to tell a robot precisely how to complete each subtask by programming it, but we also need to tell the operator exactly which subtasks the robot knows how to complete. and this here is shared knowledge. How does hierarchical meaning fit into this? Well, if the robot presents an interface of discrete operations with parameters that tell us, this is what I can do. If you look into the bottom right, I can set the switch state to be on or off, for example. Then we can take those fundamental discrete operations and we can wrap them in a single sentence, a basic English sentence, which operates on those parameters. So for example, we might wrap it in a sentence which says, set the switch state to some value, a Boolean value, either true or false, B. Now that's not natural English, it's a slightly structured English, but on top of these basic sentences, we can now place defined sentences, where the meaning of those sentences is defined by a combination of these basic sentences. So now we have two sentences, one which turns the switch on, one which turns the switch off, both in natural English. This way, every sentence can be understood by an operator, but it also means that every sentence has an unambiguous meaning to the robot, and the knowledge is shared. I'm conscious of the time limit on today's presentation, so I'm going to be moving through this slide quite quickly. But essentially what we have is just a further example of how we can abstract away from basic sentences, but this time in the context of robot planning and execution. So starting here in the green box with a simple command of moving a robot to a pose or a position and orientation. We can abstract away from that towards this green box here, moving the robot a certain distance in a certain direction. Notice that the yellow box underneath it still contains that fundamental basic sentence of moving a robot to a pose. And we've just moved and abstracted up one level from that. And we can do that again, and we can keep abstracting upwards to the point where the sentences become useful for operators. Now the operator can say, I want to move the robot 5 centimeters towards some specific object. So that was a small graph. Here on the right-hand side of this side, you actually see that this can become quite complicated. This is a very large graph with lots of levels. So how exactly does it help us? How does it aid with procedural knowledge sharing? Well, first of all, using this framework, the tasks that our system knows how to execute are all written in English, not in code. And that means they can be queried very easily by a non-programmer using a simple search function. And the documentation can easily be shared. As I mentioned, the tasks are all unambiguous, no matter how high level. So every single high level task can be understood in terms of basic fundamental tasks. We also have some basic language structures, which enable scripts to be written with conditional execution of the tasks. So, if the switch is on, turn the lights off. And you'll see an example of that on the next slide. And finally, all of the system control is operated by a subset of basic sentences. And if we handle safety at this level, then operators can be concerned with completing tasks and not programming safety conditions. So, briefly, how does hierarchical meaning help us to improve efficiency in robotic systems? Well, I mentioned scripting, and here's an example script on the right-hand side for performing some basic pick and place tasks alongside a GUI, which allows the operator to interact with the system. Automation typically has a high barrier to entry, and through natural language scripting, which can be performed by domain experts, we can reduce this barrier. Furthermore, sentences can be associated with other types of interaction, such as voice or clicking, and this enables us to build better user interfaces with common commands at the operator's beck and call. And finally, operators can actually shape their own command system by creating a sentence to do a task that they want to complete and then setting the button to execute that sentence, enabling them to quickly perform the tasks that they need to. How does hierarchical meaning enable reconfiguration? Well, like I said, the UI itself can actually be reconfigured by the operator to suit the task at hand. With scripting, new tasks can be quickly incorporated into any system. A hierarchical meaning approach also enables you to take the underlying robotic system and put a new underlying system in, and all you need to modify are the basic sentences at the interface. And this means that scripts are easily transferred between different platforms. And lastly, the last question is kind of how does hierarchical meaning support human teamwork in the operation of a robot? Well, sentence meaning being written in English can be universally understood. And the sentences themselves actually are the documentation. So this is automatically maintained. It's always available to the whole team and is easy to read. Sharing of information in natural language is also intuitive, and it's how we all communicate all the time. Structured English, in this case, isn't a pure natural syntax, but it isn't significantly more formal than in many other professions, such as the aviation industry, and it's far easier than trying to communicate a line of code to someone. So that's all from me on hierarchical sentence meaning and natural language programming. I'm quickly going to move on to part 2.3, which is remote handling through virtual reality interactions with a couple of videos. So despite the principle of scripting trying to be made as simple as possible, no one that I've ever met has sat down and written a computer program to control a robot from scratch and had it work the first time. It really just doesn't happen. So while the scripting interface is very useful that you see on the right hand side here with the robot, we also we think that's a little intimidating to a first time user. So we provide a console, which I think Sandor showed the video, but I'll play it again for you on the left here. So you see the operator typing in a sentence, move the robot to an object. So the location of the object, calculated using the image processing that Mohammed talked about, is then passed to the system, and the robot computes a motion plan to move to the object. If the operator types in a different sentence, asking it to move to a different object, the robot computes that in real time and executes the sentences one by one. And this makes it easy for the operator to kind of iterate through sentences, test out what they do. And they can also interact with the virtual reality by clicking on objects so that they can see, okay, that object is the bolt, I want to move to the bolt, or that object is the cone, I want to move to the cone. Apologies if I don't have sound activated, but this next video shows an alternative composite user interface. But here, instead of typing, voice commands are being given using Amazon's Alexa. So I'll play it for you and I hope you can hear the sound. So if you couldn't hear it, it was my colleague Ian instructing the robot to move to the object that's been selected on screen, which is very analogous to us pointing at something in the real world and saying to someone else, hey, pick that up. So by providing the context of pointing, we don't actually need to specify in language what that, in the terms of pick that up, actually is. And this allows us to create sort of more natural interactions. Taking that in the context of sentence meaning, we can use the clicking or pointing in virtual reality to populate the objects in a sentence and allows the operator to create complex commands that are quite easy to actually execute. I think that is everything on remote handling through virtual reality. Like we've said, I think questions will be at the end, but put them in the chat if you've got any for me and I'll take a look at them. And now we're going to pass over to Dr. Anthony Rossiter, who's going to talk you through part 3.
Okay, good morning. I've just got to see if I can share my screen properly. Is it this one? We'll know in a minute. Has that worked?
Yeah, that's great.
Yeah, okay. So actually what I've got to say is analogous to what James has just said. So these first few slides we'll probably go through quite quickly. And the key issue is reconfigurability by operators. So one of the challenges is how can we make operation efficient for the operators? Right, is that working? Okay, so what we're going to do is assume that the whole of the remote handling is organized around these devices that James talked about, this hierarchical meaning. So what we've got to do is construct a whole number of sentences which capture the language we use to communicate with the robot. Now that language should cover everything from movements to object definitions and so on. And once we've got that language, we can now communicate efficiently. And you'll see here, the key thing is that we use computer programmers behind the scenes to program the language. The operators do not need to get involved in the detailed programming. What they need to know is what is the language. So it's a bit like learning a language, but as you've seen, we're using English, so largely it should be straightforward. And so all that operators need to do now is get practiced at using the language or the sentences in order to operate the system. Now, this is just a screen dump of some of the S English language, and I've shown it here just to demonstrate that what the programmers need to do is define in advance what sort of things do we need in our language. So for example, here with an object, how do we define an object? And they basically have to come up with a suitable ontology, but I'm not going to discuss that any further. Now, here's the key thing, reconfiguration. Operators can still change certain things, and I'll give an example in a minute, and that's the key point. So for example, what if they wanted to change signal processing? So you might be using a particular signal processing algorithm for your image processing. What happens if they wanted to plug in a different signal processor? How might they do that? Okay. What if they wanted a new device? How would they plug in a new device? So I've got a very simple illustration of how this might work. So one of the words in English that we use a lot is fetch. Now, in this system, fetch means something in particular. It's been programmed, but you could change that word fetch. Okay, you could have fetch 1 and fetch 2. So in terms of a sentence, the operator could just replace fetch by fetch 2, and it would do something slightly different. I've got in my sentence, I've got object, and you saw James' example, he had a bolt and a spring. So the operator can change the word. Instead of fetch bolt, they could put fetch spring. I've got another bit here from the table. It's telling it where to go. Well, it might not be the table, it might be the shelf. So it's very easy, again, you see for the operator, to create a new sentence. And you see at the end, I've put something like using method A, and that might be analogous to signal processing. But hopefully you see the point here that once you've created the language, and here I've given you a simple sentence at the bottom, you can see how easy it is for the operator to use that language and reconfigure and do something slightly different. Okay, so what about high-level instructions? So I think the key thing we need to reiterate is that the operators do not need to get involved in the detailed programming. Okay. And we're going to have to make certain assumptions. So what we're going to assume, and you'll see this is in the first sentence, is that offline and in advance, you are going to have to define the appropriate language for the work area that you're working in. Okay, you're going to have to define what sort of robotic movements are likely to be needed and make sure that your sentence structure and your language has included that. And similarly, conventions for object description, you're going to need to make sure that all of the object descriptors that might be needed are set up in advance. And therefore, the operator now only needs to work with a predefined language. Okay, so in conclusion, what is it we're recommending? And perhaps I'll put the last one down here. This is the key thing. We need a shared understanding of meanings. And what we want is that shared understanding to be as simple as possible. And once that shared understanding is there, it's fairly easy for us to abstract away. So if I say fetch, you all know what it means. And that's a fairly abstract concept. And then you can apply it to concrete things, fetch the bolt, fetch the spring, and so on. I don't think I need to say any more here. It's probably going to get repetitive and we're getting short on time. So operator training, this bit's going to be very, very brief. So far, our project has not considered training in detail, but I'm sure you'll realize this is going to be critically important eventually. Okay, so what we're going to do here is briefly outline the sorts of things that might need to be done. And you'll see the point 3 I've put at the bottom. We're particularly keen to work with some of our other partners on the design and evaluation, because ultimately our scheme is going to be used alongside some of the robotics and other skills that the other partners are generating. So this gives a list of the sorts of things that you might have to think about when you're doing training, and I'm going to elaborate on some of them, so I'm not going to go through this slide in detail. So here's one: basic functional understanding of the robotic setup. So if an operator is being trained, what are they going to need to know? They're going to need to know what are all the system parts involved and what's their functionality. Okay, they need a document that's easily updated for all the operators and accessed centrally. They need this HMD document, which is this hierarchical meaning definition. So basically, what language have you defined so that I can work with this environment? And they need a list of current commands that are available. And you'll see here a key point. Some of it might be through voice. You might be able to talk to it. Some of it might be through a GUI. Some of it might be through typing, etc., etc. So basically, they need the functional understanding, the equipment, and also the interface that they're going to use. Safety procedures, this speaks for itself, so I think I'm not going to dwell on that. You'll just get bored. Okay, they'll need hands-on exercises and certifications. So we'll have to basically design a number of exercises which they need to go through to demonstrate their competence. And those exercises will obviously grow in complexity, including things like, you'll see point 3, getting them to practice reconfiguration, adding a new device, adding a new algorithm or something of that nature. And ultimately, there'll have to be some form of examination to actually they're demonstrating their competence, and we're going to sign it off. Now, this final slide, I think the red box is the most important thing that we really need to think about, because the rest of it is repeating what we've said already. The whole advantage of the proposals that we're making here is the retention and reuse of as much knowledge as possible. So we are getting operators to use English. We're getting them to communicate in a natural fashion. We're getting them to create new commands in a natural fashion. So the key advantage of the scheme is basically making operators as comfortable as possible and as natural as possible in what they do. And how we do that is this retain and reuse of the knowledge that we've either defined through our HMND or we've already got. Now, I know I've not said every word in the slides, but I think we're pretty much at the time limit, and I know Sandor wants to give you a summary, so I will pass over to Sandor.
Well, thank you, Anthony. I just turned on my mic. I forgot it. Well, not much to say from me except to thank for my colleagues for these really nice presentations. I enjoyed them very much, and I hope you did too. And well, I'm not going to repeat now the various parts. We essentially covered a whole range of topics within HRI as it was aimed for in RAIN. And myself and my colleagues would welcome any interesting question, obviously, questions here. So thank you again for attending, and hope to see you in the future in the application of the RAIN results. Thank you.
Great, thanks everyone. They're really interesting presentations. I don't know about anyone else, but I really want a peanut butter and jelly sandwich now. We've already got a question here. It's a general question for any speaker. The question is, what end application do you see for this technology? New build glove box processes, POCO, or both? If anyone would like to answer that.
Well, this is a generic question. I quickly answered this one. The technology we presented, I mean, various bits, is really generic. So it can be used in glove boxes, processes in glove boxes, but it could be used decommissioning sites with large robots as well, multi-robots working with each other. So I don't see much limit to the application of, we rather develop technology than address a concrete problem. So that's my brief answer to that one. So it can be glove boxes, POCO, and all kind of stuff. So I leave to James the next question.
Yeah, there's a question for James. When you were talking about shared knowledge, you mentioned that verification can be handled by basic sentences. Could you tell us a little more about how this works, I presume?
Yeah, so in terms of sort of the safety of the system being ensured in the basic sentences, we're thinking about how for something, let's take an example like motion planning. This is something that's going to be programmed in C++ by a programmer, and the operator is only going to have access to, move to this position or move to this object. And so the C++ programmer can be responsible for making sure that the robot executes that plan safely. And if it doesn't do that, then throwing appropriate error codes and error conditions such that the operator can say, okay, what I tried to do isn't within the safe bounds of the system. Let me try something else.
Okay, great. I hope that answers the question. I don't know, I think this is a comment, but just saying from Steve, all in English. Somewhere in France is another team doing something very similar, but all in French. So that's interesting too. If there are any more questions, please type them in the chat now. But at the moment, they are the only questions we've had. We'll give it another couple of minutes and see if anyone has any other questions. But while we're waiting to see if anyone has, I'll just say that next week's talks is going to be a slightly different format. We're going to have different talks from different universities. So we're going to have one from the University of Bristol, one from the University of Lancaster, and one from the University of Manchester. And they're going to be looking at sensing and inspection in real nuclear environments. So that's worth coming along if you can join us. Oh, we've had another question. So what are the advantages of human language sentences compared to visual block-based programming, i.e. Scratch or LabVIEW?
Well, I tried to answer this. I haven't used much the visual block-based programming myself, but I think languages in general compete well. I mean, like programming languages, we actually write code in some languages, formal languages. And the reason we do that because visual block handling is not the most suitable in my view, and certainly experience proves that. For instance, the Microsoft Robotics Studio has come up with a Visual C, which quickly disappeared. So I think there are several articles written about that language in general competes rather well with visual design. So that's my brief answer, but it's a long story, and the details, the devil is in the details.
Okay, great, thank you. Okay, we've got a question for Mohammed. Could you tell us a little more about how the vision system you were talking about might handle an object that has degraded or changed shape?
Yes, thank you for the question. Actually, we are also dealing with a kind of probability here. So while detecting an object, we are including a probability. If the object has been detected in a high probability, then the operation will be straightforward. Otherwise, the system may give an indication to operator to check the process. That's the short answer.
Great. I missed the question there, apologies. Does perception take into account obstacles that may act as a collision hazard to the robot? Can anyone help with that question?
I can answer that. I can answer that very, very briefly.
Okay.
Yes. So the objects that are detected are just passed into a motion planner, which takes them into account when it's making the motion plan.
Yeah, that's quite right.
Okay, good.
So, it's part of the intelligence of our robots too, and I anticipate in the future that physical foresight will also be involved, not just object avoidance.
Okay, great. No more questions at the moment. Obviously, the presentations are very, very detailed and clear. People don't have any questions for you.
I've been searching for this programmation en langage naturel. I don't find anything. This is my final comment.
Well, if there's no more questions, I'll keep the meeting open for a bit longer. So if anyone does have any questions, you can send them directly to me, and I can pass them on to people, and they can get back to you with the answers. Otherwise, I guess that's all for today, and I hope everyone has a lovely bank holiday weekend. And it's just to confuse us, tomorrow's bank holiday Monday, and we'll hopefully see you again next Thursday. So thanks again to everyone at Sheffield. Really interesting presentations. Thank you. Bye.
Thank you.
Thanks very much.